What do you mean by Michael acceptor? So let's say we have one alpha beta unsaturated carbonyl CH double bond O. Let's say this is R. So basically this is alpha beta unsaturated carbonyl. So basically it's a Michael acceptor unit. Michael acceptor unit. So now nucleophile attacks here and this kind of molecular electronic displacement takes place. So when we are taught or told about Michael acceptor, we always remember this type of systems or this type of system comes into our imaginations. This is a double bond O, this kind of systems, Michael acceptor. Here I will tell you about two kind of systems that is not fall in this category directly, but indirectly they can be told as Michael receptor. You know about the system, but you don't think it in that way. For examples, let's say we have these epoxides and it is functionalized in these fashions. Look, this is not that carbonyl, but it is also behave like Michael acceptor. Michael acceptor. Here I am not telling the reaction, but just for informing the students that it's a different kind of interesting systems. Why is this called Michael acceptor? Now, nucleophile come here, it attacks here, it is going, it can break. That kind of things are taking place. So this is also a Michael acceptor. So the epoxide equipped with another allylic kind of systems is a Michael acceptor. Behaves like a Michael acceptor. So don't say Michael acceptor, it's also behave like a Michael acceptor. Very interesting examples. So epoxides equipped with allylic kind of systems. Now I will let you know another Michael acceptor. Let's say these systems. Why I am telling you Michael acceptor? If you remember, this is highly unusual for, not unusual, just it happens only for these systems. I shouldn't draw a carbonyl here. Let's say we have a positive charge here. Yeah, H. So this bond in this strained three-member psychopolar ring are very much reluctant to delocalize here. If you want to read it with more details, then you can read it anytime. And the source is this book. Is fantastic write-up is there. Jerry March. So what we learned there? If we have a strained three-member ring, these bonds now become parallel to these pure p orbitals and it can delocalize over that. Similarly, that is here this is also some delocalizing tendency, these things. Now, if the nucleophile comes here, if it attack these positions, then it is very much reluctant to do this. That is, it is also a Michael acceptor. It also behave like Michael acceptor. Why it is so much important? Let's say in examples, it has been asked, which of the following molecule behaves like a Michael acceptor? One carbon is there. Say for example, second carbon is also there. But third and fourth, they have equipped the option with these two molecules. But if you don't know the details that much to this level, we say okay, then the option one option is okay, A and B is correct, all is correct. We cannot say all is correct if we don't know. But here now see these two molecules also behaves like Michael acceptor. That's the beauty of these discussions. So now Along with these things, now I categorize this. The Michael acceptor. One is these molecules. Number one, number two, epoxide installed with allylic group. Number three, yeah. So these are falls in the category of Michael acceptor. There are so many Michael acceptor also, but I am not going to discuss because of time. Just will keep it remember about these things. Secondly, you also know this. Just I am going to explain a very simple reaction, routing reactions. So basically, what happens? Let's say we have these things: NH2, C double bond O, double bond O, double bond O, OET. So we have treated these compounds plus EP3 plus. Actually, I should write it in a reverse way. Double bond CH2, as it's a double bond CH2. You shouldn't write this plus. So now we know the product easily. So as this carbon is there, now there will be a formation of alkene. Now the question comes, which alkene it forms? Look, so this is less reactive because the nitrogen lone pair takes part in delocalization and decrease reactivity. For some same logic, this is also less reactive. So it's left only one carbon. That's why the reaction will happen H2N C double bond O double bond CH2 double bond OAT. Basically, it's a chemoselective insertion of double bond. It's a terminology you should remember, you shouldn't forget. Chemoselective insertion of double bond. Now, if I asked you, so can you prepare this alkene using Utic reaction? The answer is very simple. Yes, we can of course do it. We have to take an aldehyde like that. Then we are going to take an Utic reagent plus CH minus and CH3. Basically, it will on cis directions. Just I should not say about the stereochemistry, but we have learned that if this is a stable ylide, it produces, let's say, CH3. Yeah, it is a if this is stable ylide, it forms trans. This is not stable ylide, it's unstable. I shouldn't say unstable, it's quite less stable than the corresponding stable ylides. So it will form the cis product. So now, if I say you, so can you make it a regioselective? Means can you do it on a regioselective way? Let's say CH3, CH2, double bond CH2. Then what to do? We'll take help from the same. We'll just use the same Utic reactions, but in a regioselective manner. That's why the slight change in the mother molecule selections. CH3, CH2, CHO plus CH3P plus CH2 minus. Very simple things. So by choosing our ylides or corresponding aldehydes, we can make this reaction regioselective also, or we can perform this reaction in regioselective manner also. Means where we need the double bond, we can play with that by choosing our reagent. Yeah, another thing also we can do, that is if we keep look on this CH3, CH2, CH minus, PPH3 plus HCH2. This also leave these things. Very fantastic. So we can play with the regioselectivity of the alkene. Where I am going to, where we want the double bond, according to select our starting materials. Next. So we have many examples, but because of time, I have to just stop at some point of view. We cannot discuss it at that time, at that much. Okay. Now, just I am going to show you how we can prepare different kinds of ylides. For example, let's say it is given here OCH2 Cl. Then apply PPH3. It's a very good nucleophile. So we'll have Cl will leave. I'm not showing it here. So basically this is OCH2 PPH3 plus. And secondly, this is one type of reagent. Second reagent is that PHLi. So it will abstract a proton, and what will happen? Now we are moving this will be minus. That means these things. CH double bond. Why we are discussing the utilization is very much important. A lot of questions asked from these reactions. Then we can apply one aldehyde here. CHO. Just we'll have these alkenes. It means that why I am discussing it, CH double bond PHH, because normally when I say the routing reagent, normally it comes that this is CH2, CH3 minus, we don't care about this part. So this part may have this kind of versatility. That's why I put it. Now, here I will ask a very, if I ask a very tricky questions, when we treat a routing reagent or ylide with aldehyde, the aldehyde become normally, it's a normal, either this become aldehyde or become carbonyl. Now, if I ask it, what will happen if we have this kind of systems plus Ylide? That's a good question. For this, normally we do not practice, but here we will do it. So, here, let's say we have these things PPH3, P plus, and just draw it in reverse way. Again, I'm sorry that it's basically very much interesting topic. One of the basically the Utic reaction need more than 3-4 classes. But this is so much beautiful examples. I cannot resist myself to show these fantastic examples. That's why today I will spend quite more time again on Utic reaction. CH to minus, and we have this alpha beta unsaturated carbonyl. Then it will attack here. I am explaining why it will attack here. This is what we'll have. This is O minus and this is pp3 plus, and this is pp3 plus. Okay, then what will happen when it will come back? Sorry, so basically the arrow will be here. I think when it will come back to attack here, it will leave. Means what? We'll have these things. Double bond O, yeah, these things. So what is the beauty here? The beauty is that I told about a different Michael acceptor, right? So this is one Michael acceptor. We are converting it into another Michael acceptor. This is one type of Michael acceptor, because in the very first slide we have read that this also behave as a Michael acceptor, because this bond is, or this bond you can say, is very much, as carbonyl this side I said this bond is very much reluctant to be the part of delocalization of this system. So this is one type of Michael acceptor. Let's say write MA. This is another type of Michael acceptor. Another types of MA. Michael acceptor. Now come to the part. You will say, so what is happening? Why it is attacking here? Why it is soft? Why this is not that much hard? Because it is not stabilized that much, but you are as if you are writing it that soft. Because now, if you think about the system, that phosphorus after the sulfur. So, like sulfur, not like sulfur, unlike sulfur, the sulfur has quite larger site. So here will be delocalization will be quite better than phosphorus, quite sulfur, quite better delocalization. This delocalization will be quite better than sulfur, because here sulfur the size was large. We will have just mismatch in orbitals. That's why, as is a good delocalizations up to phosphorus, then the charge density of this carbon is quite low. That's why it is soft in nature. That's why we'll attack this subcenter. That's the reason. Then we'll ask, okay, sir, if this is true, you are telling that in phosphorus, because the phosphorus is quite smaller size than sulfur, and for case of sulfur, the size mismatch. I mean, sulfur and carbon 2p orbital will be quite not good. That's why the delocalization will not be that much effective like phosphorus. So sulfur, we can designate them, or you can expect them it will be quite hard than phosphorus. Then if you use sulfur ylide, then it's supposed to attack here. The logic is that. So if we have sulfur ylide, then we expect that CH2 minus will attack carbonyl group. Based on this discussion, you'll ask or you'll predict. Let's see what happens. So we have this ylides now, Ag2S plus CH2 minus. If I write it here corresponding, PH3P plus CH2 minus, this delocal is quite better, because phosphorus has quite smaller size than sulfur. So size mismatch is more in both case size is not properly matching, but yet in sulfur the mismatch is more. That's why charge density, if I ask you where is the negative charge density more, on this carbon or on this carbon, it delocalizes quite faster, quite effective than the system. So it will have more charge density. Is here less charge density. Here quite more charge density. That's why it's quite softer. This is softer in nature. This is quite harder in nature. So now we have allowed this system to react with, let's say, let's draw the structure in better way with these systems. So as our discussion, this will attack here and we'll have this system. This is O minus and this is our this CH2 Me to S, now S plus to Me, and we have this double bond here. Now what will happen? This O minus will attack here and this will go. As a result, what we are getting? So this is double bond. These things here we are getting an epoxide. So basically same thing. So just on the variation the from sulfur to phosphorus we are getting different product. Okay. So basically this is quite irreversible. This step is irreversible. Irreversible. Why it is irreversible? Just I am explaining later. If some step is irreversible, then normally the products become thermodynamically less stable. As this is irreversible, this product will become thermodynamically less stable because in a irreversible way you always get kinetic product. This is thermodynamically less stable or less stable. So if the question is asked in a very in a complex manner, so they have given an example which is true the following fact. They are not asking the product. They are given just these two and asking what is true. Then you have to write the statement for this step. It is irreversible and thermodynamically stable product. So if you know in a very deeper way, then you can answer this type of questions. That's why I am asking it later. And what is this? Look at the new terminology. During amino acids discussions, what we said, if you have a cation and anion means the C double minus and NH3 plus, we tell them zwitter ion. Look, this also have one minus and plus. On that point of view, it also is zwitter ion. So you are also using the term zwitter ion in case of Utic reaction. Zwitter ion, which type of zwitter ion? Kinetically favorable. So kinetically favorable. Kinetically favorable zwitter ion. Now you do the same reactions with these Ylides. So we had this carbonyl. So this Ylide. Me to H double bond O, CH2 minus is plus. Now this can be a part of this extended delocalization, this kind of extended delocalization. If this is a part of extended delocalization, then what will happen? This is quite stable Ylide. And if become a stable Ylide, then if the Ylide has no stability, after making the first complex formations, the initially formed intermediate will try to come back because they know I have my one of the starting metal is stable. That's why. So just surprisingly see what I am doing it. Previously I used one arrow. Here also I am using another backside arrow. Why? Because this is reversible. Why this is reversible? Again my logic, my favorite statement, molecule is very clever. So they are forming an intermediate. Normally intermediate become unstable. So they can go to the forward side. And they also know one of my starting material is quite stable. That's why they are coming back. That's why this is reversible. And again, you see that now the fantastic things. So here, like phosphorus, we have extended delocalization. That's why charge density on carbon is quite less. As the charge density is less, its behavior is softer or soft center. If this is soft center, then this minus will attack here. Very much interesting. In one case of sulfur, it was hard, that's why it attacks at hard center. Same thing, sulfur, just we have installed the sulfur, one, just we have made this about sulfoxides. Then what is happening is become softer because of the extended delocalizations. That's why it will attack now these centers. So what is here now? So this is S double bond O Me2 plus. This is O minus, and once it comes back, sorry, one carbon more here. This will be one carbon more. Yeah. Yes. So what we are going to get? Double bond O. Basically, this is as these reactions proceed through a reversible path. This is thermodynamically more stable. This is very interesting example. Again, this is the deuterion, thermodynamically favored deuterion. Favored deuterion. In the questions, if we hear about the name deuterion in the Utic reaction, we no need to confuse. It's okay, it's quite normal there. So, if this reaction is also given and asked that which is true about the following fact, this is reversible. That's why its corresponding intermediate deuterion is thermodynamically favored and the product is thermodynamically favored. So if now the question is making it more complex, these two reactions are given and nothing is there, and they have given just these two products. Now they are writing description of two products, which is true and which is false. This product is kinetically stable, this product is thermodynamically stable in A or B written, or one option is there now, nothing is true or something more. So you have to say, okay, A or B is correct. That's why we need to understand the reaction with very depth and details also. Okay, so now we'll see the next example. Okay, let's say if we see double bond O, we want to incorporate one double bond here, then what we can do? Let's see it. This is double bond O. We have to use one base OET minus. Then let's add, you know this very well, SPH. Now it will generate the anion here. Let's minus, and this is going to attack on the sulfur sigma star orbitals, and this is going to break. So we have these things. Now, if we oxidize this by NaIO4, we will generate a sulfur epoxy pH. And then what will happen? Basically, if I rewrite them in this fashion, double bond O S O minus plus pH. Now look, here we have a concerted cyclic four-member intermediate. It will go. So if the reagent combination is given, sometime in reagent chemistry they ask about some reagent combinations. From these reagent combinations, we can say that okay, so this may be the product. So this, and then just followed by NiO4. So if you read it together, or write it together, this one will have some base, two, we will have these things, on three, NaIO4, and number four condition heat. Then we will get this product. Okay. And just for one information, if this step is modified by, for example, you know these things, you know this, an exam, they have just asked in quite different way. If we have double bond O carbonyl, then in this is Et3N in presence of base, trimethyl silyl chloride will have these things. This is O Si Me3, just these things. And then just simply normally do the what we discussed previously. Here we'll have new SPH bond, we'll have these things. Uh, it will have O Si Me3. Now if we use one zinc chloride, it will coordinate with this silica and will break it. Now this is double bond O, again something, just ignore, just consider this part as slip of the pen, because when we write cyclohexane ring, automatically because of some reflex action the circular systems come inside it. Okay, so we have now these systems. Then use NaIO4, double bond O minus, hit it, we'll get corresponding alpha beta unsaturated carbonyl compounds. Okay, here I'll show some another application of these sulfoxides. So what will happen? Here we have this kind of sulfoxide. Let's say it is S double bond O. We have this minus. It's like a stable ylide. Then normally when we have stable ylide, we always remember, okay, now there will be some carbonyl group for this attack. But see, if it is not there, let's write it in quite a middle part. If we have these things, this beer. Now this can attack here and this can the bone will live, and we will have this kind of systems. This is CH2, 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 3 carbon, and we'll have one more carbon here. These things, just if there is just counting in carbon, just ignore that. You do your on your way. Just I am trying to show what may happen. Now see, this is that system. One, two, three, four, five. This kind of system that we have seen here. This kind of similar systems. Then what will happen if we hit that system? This kind of things is going to happen. So you will have this product. That is basically, if you read it, you already have read it. This is called Chugev reaction. Reactions means here I'm trying to explain how we can use these things in various domain. Another thing, I'm here showing you. Basically, here I am taking different example and showing versatility of reagent because this is so many interesting. Now I have to fight a lot, which I will show you and which I will not. That's the difference. Because if we start this chapter at least 1 month before or earlier, we'll end up with a fantastic lot of examples. So if we use one base here, so this is acidic in nature. Why this is acidic in nature? Because this corresponding negative ion will stabilize both the carbonyl group and both the sulfoxide group. This is the highly acidic in nature. So in presence of base, one negative charge will be there. And then if I use MEBR, then what will happen? This is Me. Look, this is highly acidic because the negative charge delocalized over here. So after incorporation of one methyl, one proton is there also, one hydrogen is there also. That will be also abstracted by this H minus, and basically we have to use 2 millimoles of or P equivalent of methyl bromide. We will have methyl here. So we will end up with these things and sulfoxides. Now you have to remember it now. If we use zinc acetic acid, basically reducing conditions, in these conditions, this moiety will go away. Basically, this is the product. So basically, I'm covering from many books. That's why it's quite taking its time for me because I didn't get any time today to collect it in all one place together. That's why I have to look after the things also. But keep the hold your patience, you will learn fantastic things. Okay. Now, as a part of Uti reagent, what used, we have used this kind of Ylide, Me2S plus, CH2 minus. Also, we have used this kind of Ylide. Basically, this is sulfoxide and CH2 minus. Now, I am going to show you a different kind of Ylide that we have not used earlier. This is S plus, yeah, these things. Here it is pH and pH. This is minus. So this basically Ylide. It's not about anything strange. Now I will show you, as I have told that this may be Ylide. Let's draw it in this directions. S plus pH, pH. Now I'll show you, as we are doing reagent chemistry, how to synthesize this thing. That we can synthesize this thing also, and that synthetic part will include a lot of interesting steps. So first step, what is that? Low 1, 2, 3. So basically we have 3 carbons. So we have to start from such a precursor that contain 3 carbons. Look, so this is 1, 2, 3. 3 carbon here. So I have put bromo here and chloro here. Then what we will do? You know, this thing is a good nucleophile, so it will attack here and here will go. Then we have these things. pH2S 1, 2, 3 Cl, 3 carbons. Now we know that this is highly acidic, because if this become acidic as carbon, because the negative charge can delocalize over this. So as we have installed these things, the acidity of this hydrogen increases. This is acidic hydrogen. Acidic hydrogen. So then what will happen if we treat this with a base, let's say butyl lithium. If we use butyl lithium, we have to use one dry solvent. I am not going that part. pH2S, this is minus. Look, so what is happening there? This is going to attack these things by intramolecularly, like, and this reaction is entropically favorable because one molecule is going to divide into two things. So what we are getting? We are getting these things. So if I write it in this fashion, this is sulfur. Sorry, let me write that. So we are going to get these things. Is, yeah, Cl minus. Means let's rewrite that, the structure. pH, pH plus. Okay. Now it is highly acidic, because you know that this proton is 3 number is highly acidic. There, if we use a base like KOH, look how much the acidity extent increases. If potassium hydroxide can abstract this proton, so it's amazing. This is pH, pH, and we will have as desired this thing. So here, not only I told you that this is an Ylide, I told you that how we can prepare the Ylide, that also I have described. So what will be the name of this Ylides? This is diphenyl sulfonium cyclopropyl ylide. So what is the name? Diphenyl sulfonium, just write P, because someone tell us it is F and some people write it P. Diphenyl sulfonium cyclopropyl ylide. Cyclopropyl ylide. Okay, good. Now you will ask me, okay, sir, you told that this is an Ylide, and also told that how we can prepare this. Then why you are not showing the application of this Ylide? Okay, also we'll go to that part. How we can use these Ylides. Let's say we have these carbonyl compounds. We are treating this with these things, this Ylide. pH plus minus. So what will be? The things are very much simple. I'm just doing just in one step. So what happened? We know that there is epoxide formation here. So there should be these things. So here we will have epoxide formations in this center. Just rewrite it in that way. Just I'm telling you, we had these things, and to make our life easy, these centers look these things. Here I am. This epoxide will form, and it is very well known chemistry. And here, as a part of R, this group will present here. And if we use lithium BF4, this part we know, then I am going to show what will happen in place of lithium BF4. So we have this complex ready. Now we are using BF4. Then what will happen? This is O. Boron will coordinate with this, or oxygen load will coordinate with this F3B. So this is minus, now this is plus. So reactivity of the center epoxide now has increased. And look, another fantastic thing, that the here we have two fused three-member ring that is highly strained. Highly strained. Highly strained. So as a result, what will happen? Now, basically, this bond will break, and let's say this breaks. If this breaks, how will be the conditions? Now one plus is there. We have these things. Here we have O, PF3, and here we have the strain three-member ring. Then what is going to happen? This will attack here. As the result, what are we going to get? We're going to get 1, 2, 3, but one four-member ring here. Just one four-member ring here. And basically, here will be formation of these BF bonds. So now this will act as electronic push. At that time it will break. Basically what? We have a four-member carbonyl group. Means here. And this is double bond. When you see, just see it carefully, patiently, you can correlate these things. So what we did, we saw first that this also can be Ylide. Then we saw the synthesis of this Ylide. Then also we saw one application of this Ylide also. That if we want to transform a complex transformation, for example, this to this. Basically, this looks like a Fearing transformation, but not at all. It's a Fearing. A simple Wittig reaction followed by the breaking of these epoxide rings. That's why the reaction is very much interesting. Okay. Okay. Now Also, we know that the carbonyl group is quite reactive. Sorry, aldehyde group is quite reactive than carbonyl. So, if we have these combinations, basically, honestly speaking, I don't have a hesitation to say this to describe or to explain the reagent chemistry, the beauty of reagent chemistry in three class. It's like a offense. In three classes or 3 hour classes, you are going to explain reagent chemistry is short. It's an offense. But yet, we have to do it. We don't have any option left. Making it reagent chemistry means that you have understand all the reaction mechanisms, all the necessary things in your past 2 years or something else means all the name reaction, all the rearrangement, etc. Blah blah blah. All the SN1, SN2, these kind of things means you have learned A, B, C, D, or you have just learned the alphabet. Now means you have, or to some extent, it can be state that you have learned the grammar also. Now you are writing the sentence. When you are writing the sentence, it cannot be done so much quickly just from learning it. So basically, that's it. It takes time. Basically, whatever you have learned, we have learned in previous classes, previous years through name reaction, rearrangement. It's basically playing with that, the reagent chemistry. That's why it's quite takes time. Okay, plus pH. Look, we have one aldehyde, one carbonyl. Definitely, aldehyde is more reactive, so it will respond to the reactions. Another thing to say that it is delocalized sometimes to these systems. That's why we'll have the trans product, and just reaction will happen on this aldehydic part. So we'll have this product 1, 2, 3. Yeah, these things. It means that the aldehyde again is proof that aldehyde group is more reactive than, I should not write carbonyl because aldehyde is also carbonyl, than ketone. Then, for examples, you want to synthesis these things. For example, it has been given pH and it is asking pH. Then what to do? No need to do that much worry. Rather, it is very much simple. We'll start with this thing. This is Br. We know that triphenylphosphine is a very good nucleophile. Basically, it will replace this Br. After that, if we treat with a base, let's say N-butyl lithium, then we'll have these things. Just simply apply one aldehyde, this aldehyde, then we take reactions, we'll have these things. Very simple. Just let me couple of time. Let me have a look on this couple of books. Then I will show you more examples. Let me show you another interesting things. That is, we discussed about phosphorus we discussed about sulfur ylide. Now let us discuss the nitrogen ylide. Let's say we have these things plus pH. Look, this center is very much acidic because this can delocalize over the negative charge over this carbonyl. If you base there, what will be? We will have these things. This is pH negative dot bond OPH. So this will attack here and this will clip. As a result, basically this is what? This is basically 1 to shift reactions. This is 1 and this is considered 2 is 1 to shift reactions. So what we are getting, so we'll have, let's draw from these sides, this double bond OPH in this carbon. Now these groups comes pH and this is now nitrogen having two methyl group. Basically this is a name reaction. It's called Stevens rearrangement. Stevens rearrangement. And it goes through nitrogen kind of ylide. Okay. Another I have found another interesting examples. Let's say these things we have tertiary butyl group here. This is double bond O. Here we are treating these molecules cyclics are known with these things. CH2 minus double bond is double bond O and Me2. It's a tremendous slip of the pen. Yeah. Let's think attacks through these positions. If attack through this position, then what will happen? We will get these things. O minus, this will be CH2, this will be CH2. Now just I'm not going to write CH2. Yeah. So basically H double bond O plus Me and Me. Look what happened here. The molecule is suffering from 1,3 diaxial interactions. Basically, it's a deuteron. This deuteron is less stable. because of this diaxial interaction. Because of 1 3 how what sin diaxial interaction. Then what will happen? This is not stable. Then what? This will collapse. It will collapse to the extent. Now look, I am putting one more arrow this sides. So it will be reversible. If this is reversible, then what will we have this starting material and these things. So let us do it this fashions. This is double bond O. Now we have this now starting material CH2 minus is double bond O plus. Now this will attack in this way. What we have now these things O minus CH2 plus and tertiary butyl group. It will attack here and it will go. As a result, what we are getting? We are getting these things O, and here we have these things, these epoxides. So this is thermodynamically stable, thermodynamically more stable, dynamically more stable. And here at all if the reaction goes, that is epoxide oxygen atom lies on the axial position. And here if at all the reaction goes, then what will happen? This will end up with, it will attack there, it will go. So O, yeah, means this O projected along equatorial bond. So this is kinetically favorable. Basically, this is unstable. This is chiral control. I am not putting any attention on this product because it forms very little amount, sometimes doesn't form. We have this thermodynamic stable product. So it means that if one shot the reaction is given, what will happen? Double bond O, we have been given this Ylide. So we will have this oxygen side at equatorial position. So this is the major product.